before there were planets, before there were oceans, before there was even a place for life to begin, there was a cloud. Not a soft white cloud like the ones drifting lazily across our sky, but a vast, cold, interstellar cloud made of gas and dust. It stretched across light years, thin and nearly invisible, yet massive beyond comprehension. This was a stellar nursery. Inside it were the raw ingredients of everything that would follow, mostly hydrogen, a little helium, and traces of heavier elements forged in the cores of stars that had already lived and died. In a sense, even before the sun was born, it carried history within it. The universe had already written several chapters. For a long time, nothing happened. The cloud drifted in silence. Then something changed. A disturbance moved through it. Perhaps a nearby supernova exploded, sending a shockwave rippling through space. That wave compressed parts of the cloud, nudging it out of its fragile balance. Gravity, which had always been there, suddenly gained the upper hand. And once gravity begins, it does not stop. Regions within the cloud began to collapse. Slowly at first, then faster. Gas and dust fell inward, pulled toward denser pockets. As they collapsed, they spun, conserving angular momentum, forming a rotating disk. At the center of that disk, matter gathered into a growing sphere. A protostar. It was not yet a star, not yet bright, not yet stable, but it was becoming something. As more material rained down onto it, the pressure in its core increased. Temperatures climbed, millions of degrees. The atoms inside were packed tighter and tighter, forced into closer contact than they had ever experienced. And then, at a critical moment, the rules changed. Hydrogen nuclei, normally repelled by their positive charges, were pushed so close together that the strong nuclear force took over. They fused. 4 hydrogen nuclei became one helium nucleus. And in that process, a tiny bit of mass vanished, transformed into pure energy. The reaction ignited. Not like fire, not like anything familiar, but as a sustained, self-regulating release of energy from the core outward. The sun was born. From that moment on, it began to shine. Not gently, not passively, but with a power almost impossible to comprehend. Every second, the sun releases about 3.8 times 10 to the 26th watts of energy. Yep, that's a lot. This is equivalent to 380 trillion watts, or 380 septillion watts. That is more energy than human civilization could produce in millions of years, emitted continuously without pause. And yet from Earth, it feels simple. Warm, bright, ordinary. The sun is not solid. It has no surface in the way a planet does. It is a sphere of plasma, matter so hot that electrons have been stripped away from atoms, creating a charged, fluid-like state that responds to magnetic fields as much as to motion. Its diameter is about 1.4 million kilometers. Its mass is so large that it dominates the solar system entirely. More than 99.8% of all the mass in our planetary neighborhood belongs to it. Jupiter, the largest planet, is still tiny by comparison. Everything orbits the sun because it has no choice. Deep inside, at the core, fusion continues. Temperatures hover around 15 million degrees Celsius. Pressures are immense. The density is so high that a single cubic centimetre of core material would weigh more than a car on Earth. Here, protons collide, fuse, and release energy in the form of gamma rays. But that energy does not escape quickly. Instead, it begins a slow, chaotic journey outward. Photons are absorbed and re-emitted over and over again, bouncing through the dense interior. This region, the radiative zone, is like a crowded maze where light struggles to move forward. A photon might travel a few millimeters, then change direction, over and over again. What seems like a straight path becomes a random walk. The journey from the core to the surface can take tens of thousands, even hundreds of thousands of years. By the time that energy finally reaches the convective zone, it changes form. Here, the plasma is less dense, and heat is carried by motion. Giant cells of hot material rise toward the surface, cool slightly, and sink again. If you could see it up close, the surface would appear to boil. And in a sense, it does. The visible layer, the photosphere, is what we call the sun's surface. It glows at around 5,500 degrees Celsius, emitting the light we see. But even here, it is not smooth. It is covered in a pattern called granulation, thousands of small bright cells where hot plasma rises and darker edges where it cools and sinks. Each granule can be the size of a country. The sun is not still. It is constantly moving. Above the photosphere lies the chromosphere, a thin layer where temperatures begin to rise again. It flickers with spicules, jets of plasma that shoot upward and collapse in minutes. And beyond that, the corona stretches outward into space. The corona is vast, extending millions of kilometers, and it is unbelievably hot, reaching temperatures of several million degrees. This is one of the sun's great mysteries. How can the outer atmosphere be hotter than the surface below it? The leading explanation involves magnetic fields. The sun's magnetic field is twisted and tangled by the movement of plasma beneath the surface. When these magnetic lines snap and reconnect, they release enormous bursts of energy. It is a constant, invisible storm. The sun's magnetism gives it personality. Sunspots appear where magnetic fields are especially strong, temporarily suppressing heat and creating darker regions. These spots can grow larger than Earth. Solar flares erupt suddenly, releasing energy equivalent to billions of nuclear bombs. And sometimes the sun throws off massive clouds of charged particles, coronal mass ejections, that race through space at millions of kilometers per hour. When these reach Earth, they collide with our magnetic field. Most of the time, we are protected, but the interaction lights up the sky. Auroras ripple across the poles, green and purple curtains dancing in silence, a visible reminder that we are connected to our star in ways we cannot always see. Despite its immense power, the sun is remarkably stable. This stability comes from balance. Gravity pulls everything inward, trying to collapse the star. Fusion pushes outward, resisting that collapse. These forces are in equilibrium, a state known as hydrostatic balance. If fusion slows, gravity compresses the core, raising temperature and pressure until fusion increases again. If fusion speeds up, the star expands slightly, cooling the core and slowing the reaction. It regulates itself, a cosmic thermostat. And yet, it will not last forever. The Sun is middle-aged. It has already lived for 4.6 billion years, quietly burning hydrogen in its core. It has about 5 billion years left in this stable phase. But eventually, the hydrogen in the core will be depleted. When that happens, the balance will shift. The core will contract under gravity, heating up further, while the outer layers expand outward dramatically. The Sun will become a red giant, growing hundreds of times its current size. Its surface will cool and redden, but its total brightness will increase. The inner planets will not survive unchanged. Mercury will be consumed. Venus almost certainly will be. Earth's fate is less certain, but even if it escapes being swallowed, it will be rendered uninhabitable long before. Oceans gone, atmosphere stripped, surface scorched. After this phase, the Sun will shed its outer layers gently, not in an explosion, but in a slow, luminous release. These layers will form a glowing shell called a planetary nebula, expanding outward into space like a final breath. At the center, the core will remain. A white dwarf. Small, dense, about the size of Earth, but containing roughly half the Sun's mass. It will no longer produce energy through fusion. It will simply radiate leftover heat. For billions, even trillions of years, it will cool, fading, until it becomes something the universe has not yet had time to create. A black dwarf. And still, the story does not end. The material the Sun releases will drift into the galaxy, mixing with other clouds of gas and dust. In time, those clouds may collapse again, forming new stars, new systems, new possibilities. The atoms that once burned in the Sun may one day become part of another world, or another living being. For now, though, the Sun remains what it has always been to us, the source. Every plant that grows, every animal that eats, every cycle of weather and climate is driven, directly or indirectly, by solar energy. Even fossil fuels are ancient sunlight, stored in chemical form over millions of years. We are, in a very real sense, powered by the Sun. So when you step outside and feel its warmth, it's worth remembering what you're really experiencing. You are standing on a small, rocky world, orbiting a star, held in place by gravity, warmed by fusion, sustained by a process that began billions of years ago in a collapsing cloud of gas. The light touching your skin has crossed space at the fastest speed possible, carrying with it the story of its origin. The Sun does not know you are here. It does not shine for you. But without it, you would not be here at all. And still, it burns. Steady, relentless, patient. A silent guardian at the center of our story, holding everything together while asking for nothing in return. And so we continue, circling it in our quiet, endless waltz, round and round, bathed in starlight. Before dawn has fully stretched its golden finger across Earth's sky, before the world has even decided whether to wake or dream a little longer, Mercury has already raced ahead, looping tightly around the sun like a restless thought that refuses to sit still. It is the closest planet to our star, a world forever leaning into the light, skimming the edge of brilliance, never straying far from the sun's overwhelming glow. From Earth, it appears only briefly, low on the horizon, either just before sunrise or just after sunset, a fleeting spark that vanishes as quickly as it appears. It does not linger. It never has. Mercury was born about 4.5 billion years ago, from the same swirling disk of gas and dust that gave rise to all the planets. But even in its earliest days, something about it was different. While the outer planets gathered thick envelopes of gas, and even Earth held onto a rich mix of rock, water, and atmosphere, Mercury became something far more compact, denser, stripped down. It is small, only slightly larger than Earth's moon, but deceptively heavy for its size. Beneath its rugged, cratered surface lies a massive iron core, making up about 60 to 70% of the planet's total mass. By comparison, Earth's core is only about a third of its mass. Mercury is, in a sense, mostly core with a thin, rocky shell wrapped around it. A metal heart with a fragile crust. Why? That question still lingers. One possibility is violence. In the early solar system, collisions were common. Planets were not yet settled into stable orbits. Debris moved chaotically. It is possible that a massive impact struck Mercury early in its history, blasting away much of its outer layers and leaving behind a dense, iron-rich remnant. Another possibility is proximity. Being so close to the sun, lighter materials may have been stripped away by intense heat and solar radiation during its formation, leaving only the heavier elements behind. Either way, Mercury became what it is today. A survivor. A stripped world that endured. Despite its closeness to the sun, Mercury is not the hottest planet. That title belongs to Venus, whose thick atmosphere traps heat like a planetary greenhouse. Mercury, by contrast, has almost no atmosphere at all. And because of that, it cannot hold on to heat. During the day, when the sun blazes overhead, temperatures can climb to about 430 degrees Celsius, hot enough to melt lead. The ground itself glows with stored heat, baking under constant radiation. But when night falls, there is nothing to trap that warmth. Temperatures plunge to around minus 180 degrees Celsius, a drop of more than 600 degrees. It is a world of extremes. Fire and ice, separated not by distance, but by time. Its surface tells its story. Mercury is covered in craters, scars from billions of years of impacts. With no atmosphere to burn up incoming meteoroids and no weather to erode the landscape, every mark remains. Every collision is preserved. It is a record of violence written in stone. Vast plains of ancient lava stretch across its surface, evidence that Mercury was once volcanically active. Long ago, molten rock flowed across the planet, filling in low areas and smoothing parts of its terrain. But the most striking features are its lobate scarps, massive cliffs that can stretch for hundreds of kilometers and rise up to a kilometer high. They formed as Mercury cooled. As its core lost heat over time, it contracted slightly. The crust, unable to shrink smoothly, crumpled and buckled, forming enormous wrinkles across the surface. Imagine a planet slowly shrinking, its skin folding in on itself. A world aging in silence. And then there is the Chloris Basin, a colossal impact crater about 1,500 kilometers wide, one of the largest in the solar system. The object that created it struck with unimaginable force. The energy released was so immense that shock waves travelled through the entire planet. On the opposite side of Mercury, the surface was disrupted, forming a strange, chaotic region of jumbled hills and fractured terrain. It is sometimes called the weird terrain, a planetary echo of a single catastrophic moment. Time behaves strangely on Mercury. It orbits the Sun in just 88 Earth days, moving faster than any other planet. It races along its path at about 47 kilometers per second, a blur in cosmic terms. But its rotation is slow, very slow. Mercury is locked in a 3-to-2 spin orbit resonance. For every 3 rotations on its axis, it completes 2 orbits around the Sun. The result is something extraordinary. One full day, from sunrise to sunrise, lasts about 176 Earth days. If you stood on Mercury's surface, protected somehow from the heat and radiation, you would witness something surreal. The Sun would rise slowly, then pause, then move backward, then pause again, and finally continue forward across the sky. This happens because of the interplay between Mercury's rotation and its highly elliptical orbit. The Sun does not simply rise and set, it dances. Despite its small size, Mercury is not entirely quiet inside. It has a magnetic field. Weak, about 1% as strong as Earth's, but real. This suggests that part of its iron core is still molten, still moving, still generating a magnetic dynamo. Even after billions of years, Mercury has not completely cooled. Its heart is still alive. Faintly. Its atmosphere, if it can be called that, is barely there. A thin exosphere made of atoms like sodium, potassium, oxygen, and helium, constantly replenished and stripped away. These atoms are blasted off the surface by solar radiation, micrometeorite impacts, and the solar wind. They don't behave like a true atmosphere. They drift. They escape. They vanish. Mercury is exposed. And yet, hidden within this harsh world, there is a quiet surprise. Water. At Mercury's poles, inside deep craters that never see sunlight, temperatures remain permanently cold. These regions are in eternal shadow. Radar observations and spacecraft data have confirmed the presence of water ice there. Ice. On the closest planet to the Sun. Protected not by distance, but by shadow. We have only visited Mercury twice. Mariner 10, in the 1970s, gave us the first close-up images, revealing a cratered world that looked, at first glance, like our moon. Decades later, Messenger arrived. It orbited Mercury from 2011 to 2015, mapping its surface in detail, measuring its magnetic field, and uncovering its chemical composition. It showed us a more complex world than we expected, one shaped by both fire and time. Even now, another mission, Bepi Colombo, is on its way, promising to reveal even more. Mercury does not give up its secrets easily. It has no moons, no rings, no storms, no oceans, no sound. It exists in near total silence. And yet, it shines. To ancient observers, Mercury was elusive. It appeared briefly, vanished quickly, and never strayed far from the sun. It was hard to track, harder to understand. So they named it after a messenger, a swift traveller, a bringer of news, a god who moved between worlds. There is something fitting about that. Mercury does not shout, it does not dazzle with grandeur. It whispers. Its story is written not in clouds or storms, but in craters, in cliffs, in the quiet persistence of a world that has endured everything the early solar system could throw at it. It is a record, a memory, a fragment of the past still circling the sun. So when you glimpse it, low on the horizon, faint and silvery, easy to miss if you're not looking carefully, remember what you're seeing. A dense, ancient world, a metal heart wrapped in stone, a planet of extremes, of silence, of resilience, a small, swift traveller, a quiet companion to the sun, a world that says very little but has seen almost everything. Now we drift a bit outward, a bit farther from the sun, through a haze of light and memory, toward a world that has captivated human eyes for as long as we've been looking up. Before the stars fully fade at dawn or just after they begin to emerge at dusk, there she is. A brilliant point of light. Steady, luminous, impossible to ignore. Venus. She outshines every star in the sky. Only the sun and the moon appear brighter. To ancient observers, she was not just a planet, but a presence, a signal, a guide. The Babylonians called her Ishtar, goddess of love and war. The Greeks saw her as Aphrodite. The Romans named her Venus, after beauty itself. And yet, for all her radiance, she is anything but gentle. From a distance, Venus looks serene. A pale, glowing orb wrapped in soft clouds, reflecting sunlight so efficiently that nearly 70% of it is sent back into space. This high reflectivity, or albedo, is what makes Venus shine so brightly in our sky. But those clouds are not soft. They are thick, choking layers of sulfuric acid droplets, swirling endlessly in a dense atmosphere made of about 96% carbon dioxide. This is not a sky you could breathe. It is a sky that would consume you. Venus and Earth are often called twins, and in some ways, they are. They are nearly the same size, they have similar densities, they formed from the same protoplanetary disk in roughly the same region of space. For a moment, in the early days of the solar system, they may have looked very much alike. Two young worlds, two possibilities, two futures waiting to unfold. But something changed. Perhaps Venus began slightly closer to the sun. Perhaps it received just a bit more heat. That small difference may have been enough. If Venus once had water, oceans, clouds, maybe even rainfall, that water did not last. As the sun's heat intensified, water vapor began to accumulate in the atmosphere. And water vapor, like carbon dioxide, is a greenhouse gas. It traps heat. More heat caused more water to evaporate. More evaporation caused more heat. A feedback loop. A runaway greenhouse effect. Eventually, the oceans, if they existed, boiled away completely. Ultraviolet radiation from the sun broke apart water molecules in the upper atmosphere. Hydrogen escaped into space. Oxygen reacted with the surface. The water was gone. Forever. What remained was a planet wrapped in carbon dioxide so thick that it traps heat with ruthless efficiency. The surface temperature of Venus is about 465 degrees Celsius. Hot enough to melt lead, hot enough to erase the difference between day and night. Unlike Earth, where temperatures fluctuate, Venus is almost uniformly hot across the entire planet. There is no relief, no cool evening, no gentle breeze. Only heat. Endless, crushing heat. And then there is the pressure. Standing on the surface of Venus would feel like being nearly a kilometre underwater on Earth. The atmospheric pressure is about 92 times greater than what we experience at sea level. It presses down relentlessly. Not violently, but persistently. A constant weight. Above that crushing surface, the atmosphere moves with startling speed. High in the clouds, winds race around the planet at over 300 kilometers per hour, completing a full rotation in just a few days. This is called superrotation. The atmosphere circles Venus far faster than the planet itself rotates. Because Venus rotates slowly. Very slowly. And in a strange twist, it rotates backward compared to most planets. If you stood on Venus, the sun would rise in the west and set in the east. A reversal of what feels natural. Another reminder that Venus does not follow familiar rules. Its rotation is so slow that one day on Venus, one full spin on its axis, takes about 243 Earth days. That's longer than its year. Venus orbits the Sun in about 225 Earth days, meaning a day is longer than a year. Time there is stretched, distorted, almost dreamlike. And beneath that thick, impenetrable atmosphere lies a surface shaped by fire. Venus is covered in vast volcanic plains stretching for thousands of kilometers. The ground is made largely of basalt, a type of volcanic rock, suggesting that lava flows have resurfaced much of the planet. There are more volcanoes on Venus than on any other planet in the solar system. Possibly over 1,600 major volcanoes and many more smaller ones. Some rise high like shield volcanoes, similar to those in Hawaii, built from slow-flowing lava. Others form strange, flat-topped structures known as pancake domes, created by thick, viscous lava that spreads outward and solidifies. And then there are enormous corona, circular features thought to form when hot material from deep inside the planet pushes upward, deforming the crust. Venus does not have plate tectonics like Earth. Its crust does not break into shifting plates. Instead, it behaves differently, more like a single, continuous shell. And sometimes that shell may undergo dramatic resurfacing events where large portions of the planet are covered in lava over relatively short geological timescales. A world that renews itself in fire. Despite its hellish conditions, Venus still invites questions. Could it have once been habitable? Could there have been a time, billions of years ago, when Venus had stable temperatures, liquid water, maybe even simple life? Some scientists think it's possible. Others remain cautious. And then there are the clouds. About 50 to 60 kilometers above the surface, temperatures and pressures are surprisingly Earth-like. Not comfortable, but not instantly deadly either. In this layer, microscopic life, if it ever arose, could theoretically survive, floating in the thick atmosphere. There have even been tentative detections of phosphine, a chemical that on Earth is often associated with biological activity. But the evidence is uncertain, debated, unconfirmed. Venus does not reveal her secret easily. We have tried to visit her. The Soviet Venera missions were the first to succeed. They descended through the thick clouds, enduring heat and pressure that would crush most machines. A few of them survived long enough to send back images from the surface. The photos are haunting. A yellow-orange sky, flat, fractured rocks, a landscape both alien and eerily still. Most landers lasted less than an hour, some only minutes. Venus does not welcome visitors. Later, missions like Magellan used radar to map the surface from orbit, since visible light cannot penetrate the clouds. What it revealed was a world shaped by volcanism, by heat, by forces that operate differently from anything we see on Earth. And still, we return to her. New missions are planned, because Venus is not just a planet. She is a warning, a reminder of what can happen when a climate runs out of balance, when heat becomes trapped, when a system spirals beyond recovery. In studying Venus, we are not just learning about another world. We are learning about our own. And yet, despite everything, she remains beautiful. From Earth, she is still the morning star, the evening star, the first light in the darkness, the last light before dawn. She glows softly, peacefully, as if none of the chaos beneath her clouds exists at all. A world of contradictions. A radiant goddess cloaked in poison. A twin that chose a different fate. A planet that burns too fiercely to touch, yet shines too brightly to ignore. A beauty that does not invite you closer, but dares you to understand. After drifting past blazing stars and hostile worlds, we pause. We turn inward, back towards something familiar, something astonishingly rare. Not a distant mystery, not a hostile furnace, but home. The third planet from the sun, unassuming at first glance, yet more complex, more dynamic, and more alive than anything else we have ever found. From space, Earth is almost unreal in its beauty. A deep sapphire sphere wrapped in swirling white clouds, streaked with browns and greens, edged with ice that glints in sunlight. Oceans stretch across more than 70% of its surface, vast and restless, reflecting the sky like shifting mirrors. Storm systems spiral across entire continents. Lightning flickers within them. At the poles, curtains of green and violet light shimmer as charged particles from the sun meet the planet's magnetic shield. It does not just exist. It moves, it cycles, it breathes. And unlike every other world we have seen so far, it lives. Earth formed about 4.5 billion years ago from the same rotating disk of gas and dust that gave rise to the rest of the solar system. In its earliest days, it was anything but peaceful. The young planet was a molten world, bombarded by debris, reshaped again and again by collisions. One of those impacts, likely with a Mars-sized body often called Theia, would give Earth its moon, a companion that would go on to shape its tides, stabilize its tilt, and quietly influence the evolution of life. As Earth cooled, something extraordinary began to happen. Water accumulated. Whether delivered by icy comets, trapped within minerals, or both, liquid water began to pool on the surface. Oceans formed, and with them, the stage was set for chemistry to become biology. Somewhere in those early oceans, life began. We don't yet know exactly how, but we know it did. What makes Earth so special is not just that it has water, but that it has liquid water at the surface, stable over billions of years. It sits in what scientists call the habitable zone, the region around a star where temperatures allow water to remain liquid. Too close, and it would boil away like on Venus. Too far, and it would freeze solid like on Mars. Earth sits in the narrow middle, and it holds on to that balance. Its atmosphere plays a crucial role. Made up of about 78% nitrogen and 21% oxygen, with traces of carbon dioxide, water vapour, and other gases, it is finely tuned for life as we know it. It traps just enough heat to keep the planet warm, but not so much that it spirals into runaway conditions. It allows sunlight in while filtering out harmful radiation. It carries sound, wind, weather, and the subtle chemistry that supports ecosystems across the globe. But Earth's atmosphere did not always look like this. Early on, it was likely rich in carbon dioxide and methane, more similar to Venus or Mars. Oxygen only began to accumulate after life itself evolved the ability to produce it through photosynthesis. Tiny organisms in the oceans slowly transformed the atmosphere over hundreds of millions of years, releasing oxygen as a byproduct. In a very real sense, life reshaped the planet to suit itself. Beneath the surface, Earth is just as dynamic. At its centre lies a solid inner core made mostly of iron and nickel, surrounded by a liquid outer core. The movement of this molten metal generates Earth's magnetic field, an invisible shield that extends far into space. This field protects the planet from the solar wind, preventing the atmosphere from being stripped away and allowing life to thrive. Without it, Earth might look far more like Mars. Above that core, the mantle slowly churns over geological timescales, driving the movement of tectonic plates. Earth's crust is not one unbroken shell, but a mosaic of plates that drift, collide, and slide past one another. This motion builds mountains, opens oceans, and recycles material back into the planet's interior. It is a restless system. Earthquakes shake the ground. Volcanoes erupt, releasing heat and gases from deep within. Continents shift slowly, rearranging themselves over millions of years in a process known as continental drift. This constant renewal is not just destructive, it is essential. It regulates carbon dioxide levels through cycles of erosion and volcanic release. It shapes environments. It creates diversity in landscapes, climates, and habitats. It helps keep Earth stable enough for life to persist. And then there is water. Water is everywhere on Earth, in oceans, rivers, glaciers, clouds, and even deep underground. It moves constantly through the hydrological cycle, evaporating, condensing, falling as rain, flowing across land, and returning to the sea. It carves valleys, feeds forests, and sustains every known form of life. It is not an exaggeration to say that water is Earth's defining feature. Other planets may have traces of it, locked in ice or hidden underground, but on Earth it flows freely. It shapes everything. Life, once it began, did not remain simple. Over billions of years, it evolved into an extraordinary diversity of forms. Microbes in the deep ocean, plants drawing energy from sunlight, animals moving across land, air and sea. Ecosystems formed, complex webs of interaction where energy flows and matter cycles continuously. Forests stretch across continents, producing oxygen and storing carbon. Coral reefs build intricate structures beneath the sea, supporting thousands of species. Insects pollinate plants with delicate precision. Birds navigate across entire hemispheres, using Earth's magnetic field as a guide. Every part of the planet is connected. And then, quite recently, in geological terms, came us, humans. A species capable of reflecting on its own existence, of building tools, languages, cultures, and technologies. From this one planet came mathematics and music, philosophy and physics, art and engineering. We mapped the stars while standing on soil that grew beneath our feet. We are made of the same elements as the Earth, shaped by its gravity, sustained by its ecosystems. We are not separate from it. We are an expression of it. Earth also moves with a quiet precision. It rotates once every 24 hours, giving us the cycle of day and night. It orbits the sun every 365.25 days, creating the rhythm of seasons. Its axial tilt, about 23.5 degrees, allows sunlight to fall differently across the year, driving changes in temperature, weather, and life cycles. Its moon stabilizes that tilt, preventing wild swings that could make the climate far more chaotic. So many factors, each one subtle on its own, combine to create a world where life can not only exist but flourish. And yet, Earth is not indestructible. It has endured asteroid impacts, ice ages, volcanic catastrophes, and mass extinctions. Life has been nearly wiped out more than once, only to recover and evolve again in new forms. But the balance that supports life is delicate. Climate can shift. Ecosystems can collapse. Resources can be exhausted. For the first time in its history, one species has the power to influence the planet on a global scale, to harm it, or to protect it. We search the universe for other worlds like Earth, and we may one day find them. Planets with oceans, atmospheres, perhaps even life. But for now, this is the only one we know. The only world that sings with birdsong, that carries the scent of rain, that grows forests and coral reefs and strawberries. The only world that knows us. So before you drift off to distant planets and stranger skies, take a moment to notice what is already beneath your feet. The ground that holds you, the air that fills your lungs, the water that moves through you. This is not just a planet. It is a living system, billions of years in the making, still evolving, still changing, still carrying you along with it. You are standing on something extraordinary. Now we turn not outward, but closer. Not to a distant world glimpsed through telescopes, but to a companion we have known all our lives. The one that hangs quietly above rooftops and oceans, that follows us through childhood and memory, that has watched every human story unfold beneath its light. The moon. Our only natural satellite. A constant presence. A silent partner in Earth's long journey through space. It does not shine with its own light, yet it has illuminated our nights, guided our calendars, stirred our oceans, and shaped our imagination for as long as we have existed. Its story begins in violence. Around 4.5 billion years ago, not long after Earth itself had formed, the young planet was still hot, unstable, and frequently struck by other large bodies left over from the solar system's formation. One of those bodies, a protoplanet roughly the size of Mars, known as Theia, collided with Earth. The impact was catastrophic. The energy released was beyond anything we can easily comprehend. Rock vaporized. Entire regions melted into magma. Debris was blasted into space, forming a vast glowing disk of molten material orbiting the Earth. But from that destruction came creation. Over time, gravity pulled that debris together. Collisions within the disk caused fragments to merge, forming a single growing body. As it accumulated mass, it began to take on a spherical shape. It cooled. It solidified. And it settled into orbit. The moon was born not as a captured object, but as something deeply connected to Earth itself. A world made, in part, from the same material as our own. In a very real sense, the moon and Earth share a common origin. The moon is about 1/4 the diameter of Earth, making it unusually large compared to its parent planet. This size is not just a curiosity, it matters. Because of its mass and proximity, the moon exerts a significant gravitational influence on Earth. It stabilizes Earth's axial tilt, preventing dramatic shifts that could lead to extreme and chaotic climate changes. Without the moon, Earth's seasons might vary wildly over time, making long-term climate stability far less certain. The moon helps keep Earth steady. Its surface is stark and silent. There is no atmosphere to speak of, only an extremely thin exosphere with trace amounts of gas. There is no wind, no rain, no flowing water. nothing to erode or soften the landscape. Every impact remains. Every crater is preserved. The surface is covered in regolith, a layer of fine dust and broken rock created by billions of years of meteorite impacts. This dust is sharp and abrasive, unlike the rounded grains of sand on Earth, because it has never been worn down by water or wind. The moon's face is marked by two main types of terrain. The lighter, heavily cratered highlands are ancient, some of the oldest surfaces in the solar system. The darker regions, known as Maria, Latin for seas, are vast plains of solidified lava that flowed across the surface billions of years ago after large impacts fractured the crust. These Maria give the moon its familiar patterns, the shapes that humans across cultures have interpreted as faces, animals, or stories written in shadow. The moon's interior is much quieter than Earth's, but it still holds a layered structure. A small iron-rich core lies at its centre, surrounded by a mantle and crust. Long ago, the moon was geologically active, with volcanic eruptions shaping its surface. Today, it is mostly dormant, but not entirely. Moonquakes still occur, some caused by tidal forces from Earth's gravity, others by thermal expansion as the surface heats and cools. Even in stillness, it moves. One of the moon's most profound effects on Earth is the creation of tides. The moon's gravity pulls on Earth, slightly deforming it. The oceans, being fluid, respond most visibly. Water is drawn toward the moon, creating a bulge on the side facing it, and another on the opposite side due to inertia. As Earth rotates, these bulges move, giving rise to the cycle of high and low tides. This happens roughly twice a day. The sun also contributes to tides, though less strongly. When the sun, moon, and Earth align during full and new moons, their combined gravitational pull creates spring tides with higher highs and lower lows. When they form a right angle during quarter phases, we get neap tides, gentler and more subdued. This interplay has influenced coastal ecosystems, navigation, and even the rhythms of early life on Earth. The moon also shapes our perception of time. Its phases, caused by the changing angle between the sun, Earth, and moon, follow a cycle of about 29.5 days, known as the lunar month. The moon itself does not change shape. It is always half illuminated by the sun. What changes is how much of that illuminated half we can see from Earth. New moon, invisible, hidden in the sun's glare. Waxing crescent, a thin curve of light. First quarter, half illuminated. Waxing gibbous, growing toward fullness. Full moon, fully lit, bright and commanding. Waning gibbous, slowly dimming. Last quarter, half again, but fading. Waning crescent, a final sliver before darkness. These phases have guided human life for millennia. They shaped early calendars, influenced agriculture, and became woven into myth, ritual, and storytelling. The moon became a clock in the sky. Sometimes the alignment of Earth, moon, and sun becomes exact. When the moon passes directly between Earth and the sun, it casts a shadow onto Earth, creating a solar eclipse. For a brief moment, day turns to twilight. The sun's corona becomes visible, a ghostly halo around a darkened disk. When Earth passes between the sun and the moon, its shadow falls across the moon, creating a lunar eclipse. The moon darkens and often takes on a reddish hue, caused by sunlight filtering through Earth's atmosphere. These events are rare, precise, and deeply moving to witness. They remind us that even in the vastness of space, alignment can create moments of extraordinary beauty. On July 20th, 1969, humanity crossed the distance. The Apollo 11 mission carried astronauts to the moon's surface, and Neil Armstrong became the first human to step onto it. His words, simple and enduring, marked a turning point in our relationship with the cosmos. In total, 12 humans have walked on the moon. They left footprints in the regolith that may remain for millions of years, untouched by wind or rain. They brought back samples, data, and a new perspective. Looking back at Earth from the moon, they saw a small, fragile blue sphere suspended in darkness. No borders, no divisions, just one world. Just a couple of days ago, on April 11th, the Artemis II crew of NASA astronauts has returned to the agency's Johnson Space Center in Houston following their historic lunar flyby mission. During their nearly 10-day mission, the crew completed a record-setting lunar flyby, taking them 252,756 miles at their farthest distance from Earth and 4,067 miles above the lunar surface at their closest approach. Among the 4 crew members, Victor Glover became the first person of colour, Christina Koch, the first woman, Canadian Space Agency astronaut Jeremy Hansen, the first non-US citizen, and Commander Reed Wiseman, the oldest person to travel beyond low Earth orbit and around the moon. The moon is not just a relic of the past, it is part of what comes next. And yet, for all the science, all the missions, all the measurements, the moon remains something more. It has watched every human life that has ever existed. It has lit the paths of travellers, inspired poets, marked time for farmers, and stirred emotions that are difficult to explain. Its gravitational pull moves the oceans. Its presence moves us. It shows us the same face always, locked in synchronous rotation, turning just enough to keep that familiar side pointed toward Earth. The far side remains hidden from direct view, a quiet reminder that even the most familiar things can hold unseen depths. A constant companion, a silent witness. A world born from fire and collision. A keeper of time and tide. A mirror of sunlight and memory. You are never truly alone beneath the night sky, dear dreamer. There is always something watching gently from above, reflecting light back to you. We move outward now, leaving behind the warmth of Earth and the familiar glow of our moon, crossing a widening gulf of space toward a world that has lived in human imagination for thousands of years. A small red point in the night sky, steady and unmistakable, wandering among the stars. To ancient civilizations, it was a symbol of war, its colour reminiscent of blood and fire. To modern science, it is a world of questions, and to dreamers, it is something else entirely. It is possibility. Mars is the 4th planet from the Sun, smaller than Earth, with a diameter of about 6,800 kilometres. Its gravity is only about 38% of Earth's, meaning you would weigh less than half of what you do here and could leap higher, move differently, almost as if the planet itself were letting you go more easily. But Mars is not gentle. Its surface is coated in iron oxide, the same chemical process we call rust on Earth. Over billions of years, this oxidation has stained the soil and dust a deep reddish colour, giving Mars its signature hue like a world dusted in powdered sunsets. Yet its sky tells a different story. During the day, the Martian sky is not blue, but a soft butterscotch or salmon colour caused by fine dust suspended in its thin atmosphere. At sunset, however, something curious happens. The sky near the sun turns bluish, a reversal of what we see on Earth. It is as if Mars keeps its poetry but flips the script. Mars spins at a pace not too different from our own. A single day, known as a sol, lasts about 24 hours and 39 minutes. Close enough to feel familiar, yet just different enough to remind you that you are somewhere else. It also has seasons. Like Earth, Mars is tilted on its axis about 25 degrees, which means sunlight falls unevenly across the year. But because Mars is farther from the Sun, its seasons are longer and colder. Even at the equator, temperatures rarely climb above freezing, though on rare occasions they can reach around 20 degrees Celsius in the warmest regions. At night, the cold deepens dramatically, plunging to as low as minus 125 degrees Celsius, or even colder near the poles. Mars is a world where warmth is fleeting. The terrain of Mars is vast, dramatic, and shaped by forces both ancient and immense. Towering above everything is Olympus Mons, the largest volcano in the solar system. It rises about 22 kilometers high, nearly 3 times the height of Mount Everest, and spans roughly 600 kilometers across. It is so large that if you stood at its base, the curvature of the planet would hide its summit from view. It was built slowly, layer by layer, by countless eruptions of lava over millions of years. Mars, lacking active plate tectonics, allowed the volcano to grow in one place without drifting, becoming a giant among giants. Then there is Valles Marineris, a canyon system so vast it dwarfs anything on Earth. Stretching over 4,000 kilometers long and up to 7 kilometers deep, it would span the width of the United States. It is not a single canyon, but a complex network of valleys, cliffs, and chasms, carved by tectonic forces and possibly shaped further by ancient water. Mars is not a quiet landscape. It is monumental. And yet, beneath its dry surface lies one of its most compelling stories. Mars was not always as it is now. There is overwhelming evidence that billions of years ago, liquid water flowed across its surface. Ancient river valleys snake across the terrain. Deltas fan out where water once pooled into lakes. Minerals that form in the presence of water have been detected across the planet. There may even have been oceans. A younger Mars might have had a thicker atmosphere, warmer temperatures, and stable bodies of liquid water. Conditions that, at least in principle, could have supported life. So what happened? Mars lost its atmosphere. Unlike Earth, Mars does not have a strong global magnetic field today. Without that protective shield, the solar wind, a stream of charged particles from the sun, gradually stripped away its atmosphere over billions of years. As the atmosphere thinned, pressure dropped. Water could no longer remain stable on the surface. It either evaporated into space or froze into ice. What was once a potentially habitable world became cold, dry, and exposed. A transformation from possibility to silence. And yet, not everything is gone. Water still exists on Mars, locked away in ice. The polar caps contain both water ice and frozen carbon dioxide, growing and shrinking with the seasons. Beneath the surface, vast reserves of ice are thought to exist, hidden from view. There is even evidence suggesting that salty liquid water, brines, may occasionally flow or exist underground, especially where pressure and temperature conditions allow it. In 2018, radar data hinted at a possible subsurface lake beneath the southern polar ice cap. The interpretation is still debated, but the idea remains tantalizing. Where there is water, even in extreme conditions, the question returns: could life exist? Mars has never been alone in our exploration. Since the 1960s, we have sent a steady stream of robotic explorers to its surface and orbit. The Viking landers were among the first to search for signs of life. Later came the rovers Spirit and Opportunity, which revealed strong evidence of past water activity. Curiosity followed, a mobile laboratory that continues to study the planet's chemistry and geology. It has detected organic molecules and measured fluctuating methane levels in the atmosphere, both of which are intriguing, though not definitive signs of life. Then came Perseverance, searching for ancient biosignatures and collecting samples that may one day be returned to Earth. Alongside, it flew Ingenuity, a small helicopter that achieved the first powered flight on another planet, proving that even in a thin atmosphere, flight is possible. These machines do not feel, but through them, we explore. Mars has 2 small moons, Phobos and Deimos, irregularly shaped and likely captured asteroids or remnants of past collisions. Phobos, the larger of the 2, orbits so close to Mars that it rises and sets multiple times in a single day, racing across the sky like a restless companion. One day, it may break apart due to tidal forces, forming a temporary ring around Mars before eventually crashing into the planet. Even here, nothing is permanent. Despite its harshness, Mars continues to draw us in. It is the most Earth-like planet we can realistically reach. Its day length is familiar. Water exists, even if frozen. Its surface, though hostile, is not beyond imagination for human exploration. Plans are already in motion. Engineers and scientists are working toward sending humans to Mars within the coming decades. Concepts for habitats, life support systems, and resource utilization are being developed. The idea of growing food in controlled environments, extracting water from ice, and building shelters from Martian soil is no longer science fiction. It is becoming a plan. And yet, Mars will not make it easy. Its atmosphere is thin, offering little protection from radiation. Its temperatures are harsh. Dust storms can engulf the entire planet, lasting for weeks or months. The isolation would be profound, with communication delays stretching from minutes to nearly half an hour. It would be a place of endurance, of resilience. But imagine it. Standing on Martian soil, beneath a salmon-coloured sky, watching the sun rise smaller and dimmer than it appears on Earth. Seeing Phobos streak overhead, walking across ancient ground that once held flowing water, planting something, the first human-grown life on another world. A new chapter, written not in theory, but in footsteps. Mars is more than a destination, it is a mirror. A reminder of how planets can change, how environments can be lost, how fragile habitability might be. In studying Mars, we learn not only about another world, but about our own. What it takes to sustain life, and what it takes to lose it. A cold world with a warm past. A silent desert that once held water. A distant horizon that may one day feel close. It does not promise comfort, but it offers something else. A chance to explore, to learn, to begin again. Now we leave behind the rocky inner world and drift outward into a colder, darker region of the solar system, where sunlight softens and distances stretch wide. Out here, the architecture of the system changes. The planets are no longer small, solid bodies, but are vast, swollen giants made mostly of gas and energy. And among them, Jupiter rises above all. It is not simply the largest planet. It is a presence, a gravitational anchor, a world so massive that it outweighs all the other planets combined. If you gathered every planet, moon, asteroid, and comet in the solar system except the Sun, Jupiter would still dominate the balance. It is the fifth planet from the Sun, orbiting at an average distance of about 778 million kilometers. Its diameter stretches to roughly 143,000 kilometers, making it about 11 times wider than Earth. More than 1,300 Earths could fit inside it by volume. And yet, for all that size, Jupiter is not solid. Jupiter is a gas giant, composed primarily of hydrogen and helium, the same elements that make up the Sun. In fact, if Jupiter had been about 80 times more massive, it might have ignited nuclear fusion and become a star itself. Instead, it remains something in between. Not a star, not a solid planet, but a vast layered sphere of gas and fluid, with no true surface to stand on. If you were to descend into Jupiter, you would pass through cloud tops into deeper and deeper layers of atmosphere. The pressure would increase relentlessly. Temperatures would rise. The gas would become denser, eventually transitioning into exotic states of matter. Far below, hydrogen is believed to exist as liquid metallic hydrogen, a strange phase where it behaves like an electrically conducting metal. This layer is thought to be responsible for Jupiter's enormous magnetic field. And at the very center, there may be a dense core of heavy elements, though even this is still debated. Jupiter does not easily reveal what lies beneath. What we do see is its atmosphere, and it is anything but calm. Jupiter's outer layers are arranged in colourful bands, known as belts, and zones that wrap around the planet parallel to its equator. These bands are driven by powerful jet streams, with winds reaching speeds of over 300 to 400 kilometers per hour. Neighbouring bands often move in opposite directions, creating sharp boundaries and turbulent interactions. The colours come from trace chemicals, compounds of ammonia, sulfur, phosphorus, and other elements reacting under sunlight and heat, painting the clouds in shades of cream, ochre, rust, and gold. It is a planet of motion, a world where the sky itself is alive. Among all its storms, one stands out: the Great Red Spot. A vast, swirling anti-cyclonic storm, large enough to swallow Earth whole. It has been observed continuously for at least 350 years, though newer studies suggest it may have formed in its current state about 150 to 200 years ago, evolving from earlier storm systems. Even so, it remains the longest-lasting storm known in the solar system. Winds within it can exceed 400 kilometers per hour. It rotates slowly, counterclockwise, like a giant atmospheric whirlpool. Its colour shifts over time, deepening or fading, depending on chemical processes we still do not fully understand. It is not permanent. It has been shrinking in recent decades. But it endures. Jupiter's atmosphere is filled with storms beyond the red spot. Smaller vortices form, merge, and dissipate. Lightning flashes deep within thick clouds, far more powerful than anything seen on Earth. At the poles, enormous cyclones cluster together in geometric patterns, locked in place by the planet's rapid rotation. Jupiter spins incredibly fast. A full rotation takes just under 10 hours, making it the fastest spinning planet in the solar system. This rapid spin flattens the planet slightly at the poles and contributes to the intensity of its atmospheric dynamics. Everything about Jupiter is amplified. Its magnetic field is one of its most extraordinary features. Generated by the motion of metallic hydrogen deep within, Jupiter's magnetosphere is enormous. It extends millions of kilometers into space, forming a vast protective bubble that traps charged particles and interacts with the solar wind. If it were visible from Earth, it would appear larger than the moon in our sky. This magnetic field creates powerful auroras at Jupiter's poles, far more intense than those on Earth. These auroras are fueled not only by the solar wind, but also by material from its moon Io, whose volcanic eruptions supply charged particles that become trapped in Jupiter's magnetic environment. Jupiter is not just influenced by its surroundings, it shapes them. And perhaps most importantly, it protects. Jupiter's immense gravity acts as both a shield and a sculptor. It can capture, deflect, or redirect comets and asteroids that might otherwise travel into the inner solar system. While it does not block every potential impact, its presence has likely reduced the number of catastrophic collisions Earth has experienced over billions of years. The evidence is written in events like the impact of Comet Shoemaker-Levy 9 in 1994, when fragments of a comet slammed into Jupiter's atmosphere, leaving dark scars larger than Earth itself. Jupiter took the hit, and in doing so, reminded us of its role. Not just a giant, but a guardian. But Jupiter is not alone. It commands a vast system of moons, at least 95 known, each with its own story. Among them, 4 stand out: the Galilean moons, first observed by Galileo Galilei in 1610. They are worlds in their own right. Io is a world of fire, the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions driven by tidal forces from Jupiter's gravity, stretching and heating its interior. Europa is a world of ice, smooth and bright, with a vast ocean hidden beneath its frozen crust. That ocean, kept liquid by internal heating, is one of the most promising places to search for life beyond Earth. Ganymede is the largest moon in the solar system, even bigger than the planet Mercury. It has its own magnetic field and likely contains a deep subsurface ocean. Callisto is ancient and heavily cratered, a relic of the early solar system, preserving a record of impacts that have long been erased elsewhere. These are not just moons, they are destinations. We have visited Jupiter through machines. The Voyager spacecraft gave us our first close glimpses. The Galileo mission orbited the planet and studied its moons in detail. And today, NASA's Juno spacecraft continues to orbit Jupiter, diving close to its cloud tops, measuring its gravity, mapping its magnetic field, and revealing new details about its structure. Juno has shown us that Jupiter's interior may be more complex than expected, with a fuzzy core and deep atmospheric flows that extend far below the visible clouds. Even now, Jupiter is teaching us. And still, it holds back. We do not yet fully understand how its storms persist for so long. We are still unraveling the behavior of metallic hydrogen. We are still learning how such a massive planet formed so early in the solar system's history. Jupiter is not just a planet to observe, it is a system to study. A world without a surface. A sky without stillness. A storm that never sleeps. A giant that bends space with its gravity and shapes the fate of worlds far smaller than itself. And yet, for all its power, it asks for nothing. It simply exists, holding its place, turning endlessly, watching in its own way as the smaller worlds continue their fragile dance closer to the sun. Let Jupiter remind you that even in a universe of chaos, there can be balance, that something immense and distant can still play a quiet role in protecting something small and precious. A giant, not just of size, but of consequence. Now we move farther still, beyond Jupiter's immense gravity and storm-lashed clouds, into a quieter, colder region of the solar system. Here, sunlight fades to a pale glow, and the planets feel more distant, more reflective, as if time itself slows down. And there, suspended in that dim light, Saturn turns. Not with the overwhelming dominance of Jupiter, but with something more refined, more deliberate. A kind of quiet elegance that has captivated observers for centuries. Saturn does not demand attention. It earns it. It is the sixth planet from the Sun, orbiting at a distance of about 1.4 billion kilometers. It is enormous, second only to Jupiter, with a diameter of roughly 120,000 kilometers. And yet, despite its size, Saturn is the least dense planet in the solar system. Its average density is so low that, in theory, if you could place it in a vast enough ocean, it would float. A giant, buoyant world made mostly of hydrogen and helium, with only a relatively small proportion of heavier elements hidden deep within. Like Jupiter, Saturn has no solid surface. Its outer layers are composed of thick clouds and gases that gradually transition into denser, hotter material as you move inward. The deeper you go, the more extreme the conditions become. Pressures rise to unimaginable levels. Temperatures climb. Hydrogen is compressed into liquid and then into metallic forms. At its centre, there is likely a core made of rock and ice, but it remains uncertain in size and structure. Saturn keeps its interior hidden beneath thousands of kilometres of atmosphere. It is a world you can never truly land on, only descend into. Its atmosphere, though more subdued than Jupiter's, is still dynamic and powerful. Winds can reach speeds of up to 1,800 kilometers per hour, making them among the fastest in the solar system. Bands of clouds circle the planet, though their colours are softer, more muted, often appearing pale gold, cream, and faint amber. But Saturn has its own peculiarities. At its north pole lies one of the most extraordinary features in the solar system, a persistent hexagonal storm. This six-sided jet stream spans over 30,000 kilometres across, large enough to swallow Earth several times over. It rotates around the pole in a near-perfect geometric pattern, something rarely seen in nature on such a scale. We still do not fully understand why it forms this shape. Fluid dynamics offer some clues, but the precision and stability of the hexagon remain a puzzle. A storm shaped like a pattern, a symmetry in chaos. And then there are the rings. Saturn's most iconic feature, and perhaps the most recognizable structure in the entire solar system. They stretch outward for more than 280,000 kilometers, yet in most places they are astonishingly thin, often only about 10 meters thick. From a distance, they appear solid, like a disk or a halo, but they are made of countless individual particles, each orbiting Saturn independently. These particles are composed mostly of water ice, mixed with small amount of rock and dust. Some are as tiny as grains of sand, others are as large as houses or even mountains. They catch the sunlight and scatter it, creating a shimmering display of whites, silvers, and pale golds. Up close, the rings are not smooth. They are structured, divided into major sections labelled A, B, C, and beyond, separated by gaps such as the Cassini division. These gaps are not empty by accident. They are shaped by the gravitational influence of Saturn's moons, whose orbits create resonances that clear out paths within the rings. It is a system of balance, a choreography of gravity. And yet, the rings are not eternal. Current evidence suggests they may be relatively young, perhaps only 100 to 200 million years old. They could have formed from the breakup of a moon or comet that wandered too close and was torn apart by Saturn's tidal forces. Even now, they are slowly changing. Particles are gradually spiraling inward, falling into Saturn's atmosphere in what scientists call ring rain. Over immense spans of time, the rings may fade, thin, and eventually disappear. What we see today may be temporary, a fleeting moment of beauty in a very long story. Saturn is not alone in its dance. It is accompanied by an extraordinary system of moons, 274 confirmed so far, forming a complex and dynamic family. Some are small and irregular, likely captured objects. Others are large, active, and deeply fascinating. Titan is the largest of Saturn's moons and one of the most intriguing worlds in the solar system. It is larger than the planet Mercury and is wrapped in a thick, nitrogen-rich atmosphere. On its surface, rivers flow, lakes gather, and rain falls, but not of water. Instead, methane and ethane cycle through Titan's environment, creating a hydrocarbon version of Earth's water cycle. Beneath its icy crust, there may be a global ocean of liquid water, a world both alien and strangely familiar. Enceladus, by contrast, is small and bright, covered in clean, reflective ice. But it is anything but inactive. Jets of water vapor and organic molecules erupt from cracks near its pole, shooting material into space and forming a thin ring around Saturn. These plumes come from a subsurface ocean kept liquid by tidal heating caused by Saturn's gravity. When the Cassini spacecraft flew through these plumes, it detected the ingredients necessary for life: water, organic compounds, and chemical energy. Enceladus does not prove life exists, but it makes the possibility feel close. Other moons, like Rhea, Dione, Tethys, and Mimas, each add their own character. Some are heavily cratered, preserving ancient histories. Others show signs of past activity, with fractures, valleys, and subtle geological features. Together, they interact with Saturn's rings, shaping them, maintaining them, and sometimes even feeding them. Saturn's system is not static, it is alive with motion. Our understanding of Saturn has grown through centuries of observation. Galileo first saw its strange ears in 1610, not realizing they were rings. Later, Christian Huygens correctly identified them as a thin, flat ring surrounding the planet. Giovanni Cassini discovered gaps and additional moons, adding to the picture. But it was the Cassini spacecraft orbiting Saturn from 2004 to 2017 that transformed our knowledge. Cassini revealed the complexity of the rings, the dynamics of the atmosphere, and the richness of its moons. It watched storms bloom and fade. It mapped Titan's lakes. It flew through Enceladus's plumes. And in its final act, it dove into Saturn's atmosphere, sending back data until the very end. A mission that ended not with silence, but with discovery. Saturn does not overwhelm like Jupiter. It does not blaze like the sun. Instead, it lingers. It reminds us that beauty in the universe is not always loud or violent. Sometimes it is quiet, balanced, and fleeting. A set of rings that may one day vanish. A system of moons that continue their slow, intricate dance. A giant that moves with grace. This is not just a planet. It is a performance. One that has been unfolding for millions of years and will not last forever. Let Saturn remind you that even in the coldest, darkest reaches of space, there can be elegance. That motion can be gentle. That time can shape something delicate and vast all at once. We move farther still, beyond Saturn's fading brilliance, into a region where sunlight grows thin and the solar system feels quieter, more distant from the warmth of its origin. Out here, the planets seem less like vibrant actors and more like slow, contemplative presences, suspended in the dark. And among them drifts Uranus. It does not demand attention. It does not blaze or roar. It simply exists, tilted, distant, and strangely beautiful, glowing in soft shades of blue and green like a memory of oceans under ice. It is the 7th planet from the Sun, orbiting at an average distance of about 2.9 billion kilometers. And unlike the planets we have known since ancient times, Uranus was invisible to early skywatchers as a distinct world. It appears faint to the naked eye, easily mistaken for a dim star. It wasn't until 1781 that astronomer William Herschel noticed something unusual, a point of light that moved too slowly to be a comet and too deliberately to be a star. In identifying it, he expanded the known boundaries of the solar system for the first time in recorded history. Uranus was not just discovered, it was revealed. In terms of size, Uranus is the 3rd largest planet, with a diameter of about 51,000 kilometers. But unlike Jupiter and Saturn, it belongs to a different class, the ice giants. While its outer atmosphere is still dominated by hydrogen and helium, a much larger portion of its interior is made up of heavier volatile substances, water, ammonia, and methane, compressed into exotic, high-pressure forms. These materials are not ice in the everyday sense, but dense, hot fluids that behave in unfamiliar ways under extreme conditions. Methane in the upper atmosphere absorbs red wavelengths of sunlight and reflects blue and green, giving Uranus its characteristic aquamarine colour. It is a soft, muted glow, not vibrant like Earth's oceans, but pale and distant, like light filtered through frost. But what truly sets Uranus apart is its tilt. Its axis is inclined by about 98 degrees, meaning it essentially rotates on its side. Instead of spinning like a top, it rolls along its orbit like a wheel. This unusual orientation is likely the result of a massive collision early in its history, an impact large enough to knock the planet over and leave it permanently tilted. The consequences of this tilt are profound. Seasons on Uranus are extreme and unlike anything we experience on Earth. Each pole experiences about 42 years of continuous sunlight, followed by 42 years of continuous darkness. Over the course of its 84-year orbit around the Sun, the planet transitions slowly between these extremes. Time on Uranus is stretched and unfamiliar. Light and darkness are not daily rhythms, but generational events. At first glance, Uranus appears almost featureless. Unlike Jupiter's bold stripes or Saturn's soft banding, its atmosphere looks smooth and calm. For a long time it was thought to be relatively inactive, but closer observations have revealed a different story. Beneath that pale exterior, Uranus hosts powerful winds that can reach speeds of over 900 kilometers per hour. Subtle cloud patterns drift across its atmosphere. Dark spots, storm systems, and transient features appear and fade, often visible only in infrared or through careful imaging. Its storms do not announce themselves loudly. They move quietly, like thoughts beneath the surface. Inside Uranus, conditions become even more unusual. Beneath the outer atmosphere lies a vast mantle composed of superheated water, ammonia, and methane, a dense fluid mixture sometimes described as a slushy ocean. Under the immense pressures and temperatures found there, these substances behave in ways that challenge our understanding of chemistry and physics. One of the more fascinating possibilities is diamond rain. Laboratory experiments and models suggest that methane molecules, when subjected to extreme pressure, can break apart, allowing carbon atoms to crystallize into diamonds. These diamonds could then sink deeper into the planet, like solid rain falling through a dense, hot ocean. It is a strange image. A world where jewels form in darkness and fall silently into the depths. Uranus also has a magnetic field, but it is unlike Earth's or even Jupiter's. Instead of being aligned neatly with its rotation axis, Uranus's magnetic field is tilted and offset, as if it were generated not at the center, but somewhere within its mantle. This creates a lopsided, shifting magnetosphere that changes dramatically as the planet rotates. It is another reminder that Uranus does not follow simple patterns. Though less famous than Saturn's, Uranus does have rings. 13 known rings, narrow, dark, and faint. They were discovered in 1977 when astronomers observed a star passing behind Uranus and noticed it dimming multiple times, revealing the presence of ring material. Unlike Saturn's bright, icy rings, Uranus's rings are made of darker material, likely coated with carbon-rich compounds. They are thinner, more subdued, and more difficult to observe, like shadows tracing circles around the planet. They do not shine, they whisper. Uranus is also accompanied by a system of moons, at least 27 known, each with its own quiet story. Unlike other planets, whose moons are often named after mythological figures, Uranus's moons are named after characters from the works of Shakespeare and Alexander Pope. Titania and Oberon, the largest, orbit at a distance, their surfaces marked by craters and long, ancient fractures. Ariel shows signs of past geological activity, with smoother regions and faulted terrain. Umbriel is darker and more heavily cratered, preserving a more ancient surface. And then there is Miranda. Miranda is perhaps the most peculiar of them all. Its surface looks like a patchwork, with enormous cliffs, deep valleys, and regions that seem mismatched, as if pieces of different worlds were stitched together. One of its cliffs, Verona Rupus, is among the tallest known in the solar system, towering several kilometers high. Miranda may have been shattered and reassembled, or reshaped by internal processes that we do not fully understand. It is a moon that feels unfinished. Despite all this, Uranus remains one of the least explored planets. Only one spacecraft, Voyager 2, has ever visited it, flying past in 1986. It captured the first close-up images, measured its magnetic field, and revealed its moons and rings in detail. But it was only a brief encounter. Since then, Uranus has remained largely untouched. And yet, interest is growing again. Scientists believe that studying Uranus could help us understand not only our own solar system, but the countless planetary systems beyond it. Ice giants appear to be common around other stars, making Uranus a key to understanding a whole class of worlds. It may not be the most dramatic planet, but it may be one of the most important. Uranus does not overwhelm. It does not dazzle with brightness or complexity at first glance. Instead, it rewards patience. It invites you to look longer, to notice the subtle, the quiet, the strange, to accept that not all beauty is obvious and not all mysteries are loud. A planet tilted into eternity, a sky of pale blue silence, a world where time stretches and light lingers. Not all wonders shout. Some simply lean, glow softly, and endure. Now we reach the far edge of the classical solar system, where the sun's warmth fades into a distant glow, and the darkness between worlds feels wider, deeper, almost endless. Out here, the light that once bathed Earth arrives faint and cold, no brighter than a particularly brilliant star. And in that dim blue twilight, Neptune turns. It is the 8th planet from the Sun, orbiting at an average distance of about 4.5 billion kilometers. At this range, sunlight takes more than 4 hours to arrive, and even then, it carries only a fraction of the energy we receive on Earth. Yet Neptune is not still. It is not frozen in quiet. It is alive with motion. Neptune holds a unique place in the history of discovery. Unlike the planets known since antiquity, it was not first identified by careful watching of the sky, but by mathematics. In the early 19th century, astronomers noticed that Uranus was not moving exactly as predicted. Its orbit showed subtle deviations, as if something unseen were tugging at it. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated the position of a possible unseen planet. In 1846, astronomers pointed their telescopes to that predicted location. And there it was. Neptune became the first planet discovered through the power of theory before observation, a triumph of human reasoning. It was as if the planet had been found first in the mind and only then in the sky. In size, Neptune is slightly smaller than Uranus, with a diameter of about 49,000 kilometers, making it the 4th largest planet. Like Uranus, it is classified as an ice giant, composed not only of hydrogen and helium, but also a substantial proportion of heavier volatile materials such as water, ammonia, and methane. It is the methane in its upper atmosphere that gives Neptune its colour. Both Uranus and Neptune are quite similar in colour, a pale cyan, with Neptune having only a slightly higher hint of blue. Contrary to the rich, deep azure blue seen in many popular 1989 Voyager 2 images, modern research has shown those earlier images were heavily enhanced to display atmospheric features and were not representative of the true colour. And beneath that beauty lies something unexpected. Violence. Neptune is home to the fastest winds in the solar system. Speeds can exceed 2,000 kilometers per hour, faster than the speed of sound on Earth. These winds tear through the upper atmosphere, driving massive storms across the planet. This is puzzling. Neptune receives far less energy from the Sun than the inner planets, yet its atmosphere is more dynamic than Uranus's. The reason lies within. Neptune radiates more heat than it receives. It has an internal energy source, likely a combination of residual heat from its formation and slow gravitational contraction. This internal heat powers convection, fueling the powerful winds and storms that shape its atmosphere. Even in the cold, there is motion. One of the most famous features observed on Neptune was the Great Dark Spot, discovered by Voyager 2 during its flyby in 1989. It was a storm system roughly the size of Earth, resembling Jupiter's Great Red Spot, but darker and more transient. When astronomers looked for it again years later, it had vanished. New storms appeared elsewhere. Neptune's weather is not fixed. It forms, evolves, and disappears. A constantly changing atmosphere. The planet's outer layers are structured in bands and clouds, though less distinctly than Jupiter's. High-altitude methane ice clouds drift across the upper atmosphere, sometimes casting shadows on the layers below. Bright streaks and patches appear and fade, hinting at complex weather systems beneath. It is a world of motion hidden within subtlety. Inside Neptune, the structure becomes increasingly exotic. Beneath the atmosphere lies a thick mantle composed of superheated high-pressure fluids, water, ammonia, and methane, compressed into a dense, slushy state. Under extreme conditions, these materials may separate and reorganize in unusual ways. Like Uranus, Neptune may experience diamond rain, where carbon atoms are compressed into crystalline form and fall deeper into the interior. At the center lies a rocky core, hot and dense, though relatively small compared to the planet's overall size. Neptune is layered not just physically, but conceptually. Each layer stranger than the last. Neptune also possesses a faint system of rings. There are 5 main rings, composed of dark, dust-like particles. They are thin, incomplete in places, and difficult to observe from Earth. Some contain brighter arcs, clumps of material held together by the gravitational influence of nearby moons. They are not grand like Saturn's. They are subtle, like threads of shadow circling a distant light. And then there is Triton, Neptune's largest moon, and one of the most intriguing objects in the solar system. Triton orbits Neptune in a retrograde direction, meaning it moves opposite to the planet's rotation. This strongly suggests it was not formed alongside Neptune but was captured, likely a former dwarf planet pulled into orbit long ago. This capture may have disrupted Neptune's original moon system, leaving Triton as the dominant survivor. Its surface is icy and geologically active. Nitrogen geysers erupt from beneath its frozen crust, sending plumes of material into the thin atmosphere. The terrain is varied and strange, with ridges, smooth plains, and regions that resemble the textured surface of a cantaloupe. Beneath its surface, there may be a subsurface ocean, and where there is liquid water, even in extreme environments, the possibility of life lingers. Neptune marks a boundary. Beyond it lies the Kuiper Belt, a vast region filled with icy bodies, remnants from the early solar system. Worlds like Pluto, Eris, and Haumea drift there, distant and faint. And beyond that, the scattered disk, the Oort cloud, and the deep uncharted reaches of interstellar space. Neptune is not the end, but it feels like an edge, a threshold between the familiar and the unknown. We have only visited Neptune once. In 1989, Voyager 2 flew past, capturing the only close-up images we have ever seen. It revealed the great dark spot, measured the winds, observed the rings, and studied Triton in remarkable detail. Then it continued outward, leaving Neptune behind. Since then, no spacecraft has returned. And yet, Neptune remains, spinning slowly, winds racing, storms forming and fading. It waits, not impatiently, but quietly. A world where the sun is distant, where winds outrun sound, where storms appear and vanish like thoughts. A planet that reminds us that even in the coldest, darkest reaches, there is energy, motion, and quiet beauty. Let its winds carry your thoughts outward. Let Triton's icy plumes rise in your imagination. Let the vastness beyond settle gently around you. Because even here, at the edge of the sun's domain, the universe is still alive.